So just a reminder, everybody, make sure that you vote. The election's in like 6 days, or something like that. So please, vote. It's super important. Um, right. So today we're going to be starting talking about impulse and momentum. And we're going to finish that discussion on Friday. So let's define impulse. By the way, so today we have a lot to cover, so I probably won't be able to field as many questions as I would have liked to. So do stick around if you have questions afterwards, because I'm more than happy to answer them then. So I'm not going to define impulse yet. I'm just going to give you something to consider. So let's consider two objects collide. It might be useful to consider what they have in common. So we're not talking about the specifics of the forces or anything like that. We're just considering just the collision. So what we know is true is that the force on one object, remember I said I would use a notation like this where I put this vertical bar, by the second object has the same magnitude as the force on the second object by the first object. And that's just Newton's third law, equal and opposite magnitudes, or equal and opposite forces. And so the equal part means the same magnitude. And similarly, the time of interaction between the two objects are the same. So the time for which those forces are applied are equal. So if block 1 hits block 2 and that collision takes place over 10 milliseconds, block 2 will experience a force for 10 milliseconds. Similarly, because the collision is symmetric, like they hit each other, block 1 will hit, so the force that block 1 will experience will be the same duration as the force that block 2 will experience. So what we can do is we can define a quantity. Let me actually reorient so then I doesn't, so the audio quality is not bad, like I did last time. So we can define a new quantity. And we're going to call that quantity impulse. Somebody's microphone isn't muted. And the letter that we give it is J, capital J. And so this is defined as the force applied to an object times the duration over which that force is applied. And so in particular, this delta T is the same for both colliding objects. And similarly, this force is like for two colliding objects, the force are third law pairs. And so what that implies is that the magnitude is the same for both. And again, this is for two colliding objects. So I'm just going to put a header here called momentum, and then we're going to continue. So let's talk about what the difference. So by the way, so far I've just defined this thing, impulse, and you might understand why it's a useful thing for collisions, and that's only because the duration of impact and the magnitude of the forces are the same for each of the colliding objects. And so you can imagine that it could be useful for understanding collisions, and it'll turn out that it is quite useful. So let's talk about the differences between work and impulse. So they are different things, right? But it's useful to actually characterize the ways in which they're different. So importantly, work is a scalar and impulse is a vector. Impulse is a vector because it's a vector times a number. And the reason why I'm going over these differences, by the way, is to make sure that you don't confuse these two things. Work doesn't care about the direction of the force. And impulse does. Also, work doesn't have a third law equivalent. We talked about that with regards to like a ball falling. It pulls up the earth a little bit, but like the work done on the ball is not the same as the work done on the earth. However, impulse does. And it should be fairly straightforward to see why. Sorry, I'm going to fix my wires because they're all over the place and annoying and all that. Right. So why does impulse have a third law equivalent? Well, the force is equal and opposite. In a collision. Oh yeah, B/W is between. Sorry. Yeah. So the force is equal and opposite, and the duration is the same. So that means that the impulse is equal and opposite between two colliding objects. So the question then is okay, so we have this thing that has a third law equivalent for like two colliding objects. If the impulse that one object gives to the other object is the same as the impulse that the second object gives to the first object. So the question is how do we use it? Well, fortunately, we can use impulse in a similar way to the way that we use work to learn about mechanical energy. So let's look at the example of the books sliding on top of each other. So in this case, so remember that situation where we had the books where there was friction between them, and then they were sliding on a smooth surface. So we're going back to that example. So initially, book A is sliding to the right, and so we can actually draw force diagrams for each of the two blocks. So block A is going to experience a frictional force to the left, right? And so the impulse delivered to A is, and the coordinate system we're going to use is the standard one, to A is negative F, where F is the magnitude of the frictional force, negative F delta T in the I hat direction. So it has magnitude F times delta T, where F is the magnitude of the vector F, the frictional force. Delta T is the duration over which the book A is sliding over book B, the duration over which this force is applied. It's in the negative I direction because it's pointing to the left. And then we can do the same thing for book B. Book B will experience a frictional force pointing on it to the right with the same magnitude, opposite direction. And so the impulse delivered to book B can be written, it's just F delta T, same duration, same magnitude of force in the I hat direction. So the resulting sum of these two impulses, the impulse delivered to book A plus the impulse delivered to book B, the sum is 0. So we would write JA plus JB, that is the impulse delivered to A plus the impulse delivered to B. That's equal to 0. And so we can actually use the formula for what impulse is. Impulse is just the vector, or is the force vector times the duration of the impact, or the duration of the duration over which the force is applied, sorry. By the way, this book example is just, it's a strange example of a collision. But it is indeed a collision. You have two objects that weren't initially together, and then they interact, and then something happens. That's what a collision is. So this is equal to the force on A times delta T plus the force on B times delta T, and that's equal to 0, right? Because the sum of the impulses is equal to 0. Come on, scroll. And so we can rewrite this. We know what the force on A is. Yeah, J is always impulse. The force on A is the mass of A times the acceleration of A, right? Assuming there are no other forces, which is a fair assumption here, plus the mass of B times the acceleration of B times delta T. That's equal to 0. And if we assume that delta T takes place over a sufficiently small time, if the delta is a small change, which I'm going to assume, then this would be equal to MA delta VA over delta T times delta T plus MB delta VB. So we have to assume delta T is small in order to get this this fact, but this is just an approximation that we're doing anyway. This is equal to 0. No, so in the formula for impulse, F is the force vector. It's not a magnitude, because impulse is a vector, so it's just the force itself. See, it's a vector, not a magnitude. Right, and so we can just cancel out these delta t's. And so what we're left with is ma delta va, that's the change in speed of book 1, plus mb delta vb, it's the change in speed of book 2, sorry, change in velocity. Now, all of, yeah, these should be vectors. Change in velocity of book 1, change in velocity in book 2, that is equal to 0. And so we could rewrite this, assuming that the masses don't change. We could rewrite this as the change in MAVA plus MBVB. That's equal to 0. And so this quantity here, MAVA, oh, and those are vectors, that quantity is the mass times the velocity of the system. In a sense, and I'll be more explicit about what that means in a minute. So from this whole business where the sum of the impulses during a collision is 0, we find something new. We find a new conserved quantity, and it's not energy. So before we had energy conservation when there was no external work, and that was that the kinetic plus potential was conserved. It didn't change over time. The before and after was the same, but this is just a different thing that also doesn't change between before and after. And this quantity is the product of mass and velocity. We call it momentum. We call that product of mass and velocity. And we use and it's denoted, we use the letter P, and it's a vector because velocity is a vector, and if you multiply a vector by a scalar, you get a vector, or you get a scalar. And so in this case, P, don't ask me why we use P. This triple equal sign is defined as the mass times velocity. And we can check the units of P. Again, P without the vector symbol over just means it's the magnitude. The units of P is kilograms meters per second. So momentum, this thing momentum, is conserved, at least in some situations, like in the case of the books. The books sliding on top of each other. Now let's talk about momentum conservation in more detail. So first of all, why do we care about momentum conservation? We care about this thing momentum because new conserved quantities in general are very useful, right? You've already found from doing the homework that energy conservation lets you solve problems that would have otherwise been very hard to solve. And so just having another conservation problem, another conservation tool will be very, very helpful to solve other types of problems. And maybe we could combine it with energy conservation and so on and so forth. So let's talk about when momentum is conserved. Oops, did not mean to scroll out. One moment. There we go. Let's talk about when momentum is conserved. So in general, well, no, let me not start the sentence that way. So what, when is, yeah, it's not an equation, it's just saying P means MV. So when is energy conserved? Energy is conserved when there is no external work, right? What that means, or what I mean by that, is that if there's no external work, then the formula external work equals change in kinetic energy plus change in potential energy plus change in thermal energy becomes change in kinetic plus change in potential plus change in thermal equals 0, which means that the overall change of all of those three things is the sum of those three things don't change. And so we want a similar thing for when momentum is conserved. What do we need in order for momentum to be conserved? Well, certainly, we need a closed system, just like energy conservation. I.e., you can't have outside influences because that will affect the momentum of the system. And so by closed system, by the way, I mean external forces and things external to the system affecting the system. But in particular, for momentum conservation, we need a little bit more than that. Or rather, we can be more specific than just a closed system. We need no external impulses. So imagine in the two books example, because there's nothing else happening to the books, there's no other impulses affecting the books, at least in the horizontal direction, the momentum is conserved, right? That's what we found here. We found that the change momentum is 0. However, imagine now that you're pushing both books while this is happening. Well, then impulse is just an external force applied over a duration. So if you applied a force to the books over some duration, that could change the momentum of the system. Just like how if you applied a force over a distance, an external force over a distance, that could change the energy of the system. So the idea here is just like how when we talked about energy, anything that wasn't part of the system that was creating more of this stuff, in the case of energy, more work, that would affect energy conservation. In this case, when we're talking about momentum conservation, which we got by setting the sum of impulses to 0, we would find that if there's an external source of impulse, if there's an external force applied over a duration to the system, that would break momentum conservation. So the end result of this discussion, and it should become hopefully fairly clear shortly, is the impulse momentum theorem, which is very, very similar to the work energy theorem. So the impulse momentum theorem, it's just another equation, like you had external work equals change in kinetic energy plus stuff. This is the equation. External impulse, so the impulse that is applied to a system, external or from external to the system, is equal, well, external impulse by definition is the external force times the duration over which that force is applied. This is equal to, this is what the impulse momentum states, it's equal to the change in momentum of the system, which can be written as delta m v. So if we wanted to really like summarize it and put it in one line, it would be J external equals delta p. But I added in these extra tidbits to be a little bit more clarified. So this p is internal, or is the momentum of the system. So you would find the momentum of each part, and then you would add them together. And for a single object, that would just be, because a single object has one mass and one velocity, it would just be the mass times the velocity of that object. So in words, this is just saying that the momentum of a system, i.e. the sum of the mass times the velocity for all of the objects in that system, is conserved, i.e. it doesn't change if there are no net external impulses on the system. So consider everything in your system and then consider what's outside of your system. If the stuff outside your system is applying a force for a duration, then there might be an external impulse, in which case momentum would not be conserved. Now this makes perfect sense on a single object. And I'll explain why it makes perfect sense in a moment, or right now rather. Put an exclamation mark there. So the formula from the impulse momentum theorem gives us that the external force on the object, everything's external to a single object, right? Times the duration over which that force is applied is equal to the change in the mass times velocity of that object, right? Now, assuming that the mass doesn't change with time, which is a typical assumption, we could simplify this, or we could rearrange this to get that the external force is equal to the mass times the change in velocity divided by the duration, which is just equal to m times the acceleration for a small delta t. So the impulse momentum theorem is literally just Newton's second law. It's just a more general form of it. Now, just as a note, so when we were talking about energy conservation, there was this sense that thermal energy was a way of dissipating energy. Like you would have friction and that would dissipate energy of the system. You could lose potential energy or lose kinetic energy due to friction. Such a thing doesn't exist for momentum. You can't dissipate momentum. It just is not a sense. It's not a thing that can happen. There is no thermal momentum. And so the point that I'm trying to make by specifying this is that you really need to keep in your head kinetic energy separate from momentum. Like they're related, but they're separate ideas. Friction can reduce the can dissipate kinetic energy. It cannot dissipate momentum. So we're going back to this question of momentum conservation and when do we do it? So how do we figure out if momentum is conserved? Like really, how do we do that? How would you do it if this was a homework problem? How do you decide when momentum is conserved? And the reason why you might want to do that, by the way, is because you might want to be able to establish if momentum is conserved, then I can use momentum conservation to solve this problem, i.e. the initial momentum is equal to the final momentum. That would be a good thing to be able to write down because then you can maybe solve for the final speed or something like that. Well, the way that you do this is you just ask if all forces involved are internal to the system. If they are all internal to the system, that means that there are no external forces and hence there can be no external impulses. So oftentimes when we do momentum conservation like problems, what will happen is you'll have like two objects colliding, for example. That's like a standard momentum conservation problem. Two objects colliding. And so maybe you ignore gravity or something like that. And so because gravity, like typically, unless otherwise stated, you can just ignore gravity. In which case, you would say, oh, well, the two objects, like the only forces that are present, if I consider the system to be the two objects, would be forces from object one to object two and from object two to object one. Those are the only forces. And so if our system is both of those objects, then both of those forces are internal to the system. And so there would be momentum conservation just because there's no external forces involved. And by the way, I believe I will get to I'll finish today with an example of momentum conservation and how we can use it for these more complicated things. The impulse theorem notes section right here. Actually, I need to scroll up. I actually need to continue. So I'll just leave it like this, and there, you can at least see a little bit. So the next thing to talk about is that unlike energy, which is either conserved or not, there is this sense that you can have partial momentum conservation. So if they are internal, yeah. If all the forces are internal to your system, then the momentum of that system is conserved. So we've talked about how momentum is a vector, right? Momentum as defined is mass times a vector, and so any number times a vector is a vector. So you might be asking the question, what does it mean for a vector to be conserved? So really, for a vector to be conserved, and by conserved I mean not change as time proceeds, what that really means is that each component of the vector has to be unchanged. So when I say that momentum is conserved, really what I'm saying is the x component, the y component, and the z component are all unchanging over time. Now, because there's three components in general for a conserved vector, it's possible, or sorry, for any given vector, it's possible that one of the components might not change and the other two might. If one component, or rather, let me write it a different way. It's possible to just have one or more components be unchanged. And the way that we would figure that out what that would imply is it means that there are no external impulses in that direction. Impulses in. What I mean is, say you have a momentum vector, and you've established just by observing the object, or you're observing some system. Maybe it's like a ball flying through the air or something. You've observed the system, and you've noticed that when you calculate its momentum vector, one of the components doesn't change, and the other one does, or the other two do. Now, what that implies is that the external impulses must just not be in the direction of the unchanging momentum component. So, for example, if the momentum vector is changing in the y direction but not changing in the x direction, that would just mean that the external impulse is only in the y direction, because the force in the y direction can't affect the motion in the x direction. An example of this would be a projectile with no air resistance. No air resistance. Conserves momentum in the horizontal direction. Horizontal direction, but not in the vertical direction. So if there's no air resistance, that means that there's no forces that point left or right. Imagine like throwing a baseball or something like that. There are no forces left or right. There's only gravity pointing downwards. It's the only force. And so the momentum, the horizontal component of momentum, therefore, would be conserved because there are no external forces, external impulses in the horizontal direction. On the other hand, the momentum in the vertical direction is not conserved because there is a vertical impulse. The way to imagine this is that the horizontal speed never changes, right? If it's traveling at 5 meters per second to the right, it will continue traveling at 5 meters per second to the right, even though its verticals, the speed in the vertical direction might change. Similarly, the vertical component of the momentum starts out in the upward direction, or it starts out with some large value in the upward direction, right? But then as time passes, it slows down in the upward direction, which means its momentum gets smaller, and eventually reverses, which means that its momentum is changing. Momentum is not conserved in the vertical direction. Now, this is all great, but we do have to take a short detour in order to fully capture how we can use momentum to solve problems. So we're going to take a detour to the land of center of mass. So we have to talk about center of mass because remember when we were first talking about Newton's second law, we talked about the acceleration of the center of mass. Well, now we actually need to, we see that momentum conservation is very closely related to Newton's second law. And so if we want to use momentum conservation in a more general setting, we need to understand what the center of mass acceleration really means. So, wait a minute, what happened to my notes? They're already out of order. What? My notes are out of order. That's confusing. One sec. Let me just verify. Okay, no, never mind. I don't think they are out of order. Yeah, no, they were in order. That's fine. So before we continue with center of mass, before I actually explain what it is, let's talk about an example where momentum should be conserved. So we have a block with mass m1 attached to a spring, maybe not attached, maybe just like next to a spring, to a block with mass m2. So if there was air resistance, it wouldn't conserve momentum horizontally. Precisely, and that's because there's an external force pushing in the horizontal direction. So imagine that before, like in the initial state, we have the two blocks are pressed up against this spring, and the spring is really compressed. And initially they have no speed. And then after, then we just let them go. You have one block that has some velocity in that direction. You have the spring in the middle that pushed them apart, and then you have the other block going to the right. Now, in this situation, there are no external forces if we consider both blocks and the spring to be part of our system. So that means that there are no impulses, no external impulses. We're going to call that our system. So what this means is that the momentum should be conserved. Momentum of the whole system never changes. So in the initial case, before, the momentum can be calculated. We have m1 v1I for initial plus m2 v2I. That should be equal to the momentum after. We have m1 v1f plus m2 v2f. And these two things should be equal. Let me just write it out as an actual equation. m1 v1 plus m2 v2 should equal m1 v1f plus m2 v. So by the way, this would be an example of how you actually apply momentum conservation. Like you write out the momentum before, mass times velocity of each part, then you set it equal to the momentum after. So this is the momentum before, and this is just equal to 0, right? Because they each have 0 velocity initially. And this is the momentum after. Now, what we can establish is that the smaller of these masses, from this equation, by the way, smaller of these masses should move faster. And I think that probably aligns with your intuition. So let's just say that m2 is greater than m1. Then v1f, we could solve for v1f using this equation, right? We would solve for v1f. We would move this guy over to the left, and then we would divide by m1. So this would be negative m2 divided by m1 v2f. So, by the way, I promise we're getting to the center of mass. It's just we'll get there. This is early justification. So m2 over m1, that should be greater than 1, because m2 is bigger than m1. And so we'd find that v1 has a larger magnitude than v2, just because I mean, obviously it points in the opposite direction, but it has a larger magnitude. So that's just a simple example. However, things get more complicated when we want to talk about more complicated systems, and that's where the center of mass business is going to play a role. But let's table that for just a minute. Momentum conservation comes about thanks to Newton's laws, like all of them, first, second, and third, right? So let's talk about let's return to the second law. We're going to consider the two blocks above, like here, as a single system, just like we just did. What is the net force? The net force on the system. Well, there are no other things in our universe. It's just those two blocks. So there is zero net force, right? And we know that systems with zero net force experience zero acceleration, right? That's Newton's second law. So it seems like that contradicts the result that we just got. We just found that they start off at rest and they end up moving at some speed, right? So how could it be that the system has zero acceleration, even though the blocks are moving? So the question is where did we go wrong? And the point that I was making earlier is just is the following. Recall that Newton's second law refers to the acceleration of the center of mass. That's the important bit. So each block will accelerate, but the claim is that the center of mass will not. So let's rewrite the momentum conservation equation that we just did. We're only going to write it in the horizontal axis because it's one-dimensional motion. We can do that. To try to figure out how center of mass is defined. So we have 0, which is equal to m1 v1 plus m2 v2. That's just by definition equal to m1 times dx1, that's the position of block 1 dt, plus m2 dx2 dt. Again, we're just working, we're doing the typical thing where we just treat we're just working with one-dimensional motion, so we can treat everything as just numbers instead of vectors. And if you're careful, you'd find that this is equal to the time derivative, again, assuming the masses are fixed, m1 x1 plus m2 x2. Right? And so what that implies is that 0 should be equal to, I'm just doing some algebra trickery here, times m1 plus m2 times the time derivative of m1 x1 plus m2 x2 divided by m1 plus m2. So all I did was multiply and divide by m1 and m2 and put one of them inside the derivative because they're constant, so it doesn't matter. And so this is equal to, well, this is just the total mass. And we give this a name. We call it x sub cm, the center of mass. So this is m total times the time derivative of x sub cm. So the fact that velocities of the mass blocks are in opposite direction of each other has to do with anything? Not really. It's just v2 might be positive, v1 might be negative. They're just numbers. They can be positive or negative. And this is equal to the mass, the center of mass, sorry, the total mass times the center of mass velocity. And that is defined, and that's how we talk about the total momentum. That's what the momentum of the system is. And so the total momentum of the system is indeed 0, following through from here. So indeed, it is true that the momentum of the system, which starts off at 0, the time derivative of position is velocity. It is true that the initial momentum of the system is 0. That's just because nothing's moving initially. But indeed, even the final velocity of the system is also equal to 0. And that's just from momentum conservation, and that's okay. It just means that the center of mass velocity is 0. So this gives us the center of mass for so we can generalize this idea. This was the center of mass position here. Yeah, m tot is total mass. It's just this thing. This gives us an idea of how to generalize this idea of center of mass. The center of mass for more or for several point masses remember, we do go over today because of the quiz. The center of mass for several point masses can then be written in more than one dimension, in say 3D, as RCM. And that would be m1 times r1 plus m2 times R2. This is the center of mass location, plus M3 times R3, plus so on and so forth, divided by M1 plus M2 plus M3 plus dot dot dot. And so that implies that we can look at the components of this position vector in each of the three standard directions. So the center of mass position in the x direction is M1 x1 plus M2 x2. These are the positions. So by the way, in this case, R1 is the position of object 1. R2 is the position of object 2, and so on and so forth. And M1 and M2 are the corresponding masses of those objects, plus M3 x3, and so on, divided by the total mass. And then you could do the same thing for the center of mass position in the y direction. M1 y1 plus M2 y2 plus dot dot dot, divided by M1 plus M2 plus dot dot dot. And then you could do the same thing for the z direction. And so the point is you can define a position in space, the center of mass position, also known as RCM, that tells you basically where the center of all of the mass is. So it's almost like an average of all of the positions of the objects, but the average is weighted by the mass. So if you have a whole bunch of heavy objects over here, and then one light object over here, the center of mass is going to be close to the heavy objects. Whereas if you have a whole bunch of equally massive objects, like all spread out everywhere, the center of mass will just be in the middle of them. So it kind of just tells you, if you treated all of the objects in your system as just a single point, where would that point be? The point is so both things are right. So the total momentum of the system is 0 because the velocities are opposite to each other. But another way to see that it's 0 is that the center of mass never moves. RCM, this is the center of mass position, or also just known as the center of mass. And then VCM would be the center of mass velocity, and so on. All right, so I promised I would get to this. That was the whole point. We need to talk about the center of mass acceleration, or the acceleration of the center of mass. So think of the center of mass as a place in space that labels the center of your system. That place will move depending on what forces there are, because the objects in your system will move, so the center of mass has to move with it. So in the spring box system above, we could figure out what the center of mass velocity is before and after. So before, the total velocity was 0, like the velocity of each thing was 0, so the center of mass velocity is 0. No, so RCM is the center of mass for the whole system. After, we could also go and compute what is the center of mass velocity. Well, the way that you would do that is you would plug that in here, and you would find, you would take derivatives and you would get M1 V1 plus M2 V2 divided by M1 plus M2. You would find, after plugging in these values, that value for V1 and V2, you would find that the center of mass velocity after they spread apart is also 0. So in general, the external force is just the time derivative. This is another way of writing Newton's laws, is the time derivative of the center of mass momentum, which is just the mass times the center of mass acceleration, where the center of mass acceleration can be written as two time derivatives of the center of mass position. So that would be m1 d squared r1 dt plus m2 d squared dt squared r2 dt squared plus dot 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 divided by m1 plus m2 plus dot dot dot. And this is just another way of writing m1 a1 plus m2 a2 plus dot 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 divided by m1 plus m2 plus dot dot dot. Is the center of mass the center of mass of the system? The center of the center of mass refers to the center of mass is a property of a system. So it depends on what system you're considering. If you're considering your system to be both blocks, then the center of mass is the center of mass of those two blocks. If you're considering just one block of your system, then the center of mass is the center of mass of that one block. It depends on what you're considering your system. Right, so I do still have 5 minutes left, so I'm going to try to shove more things in because I unfortunately have more to do. I know this is a lot, and I'll stick around and answer as many questions as you want afterwards. But the whole point of this was just that there are two ways that we could visualize this. We could consider the block problem like we did, just find the velocity of one, the velocity of the other, and then add them up and so on and so forth, and we could solve the problem. But that seemed like a contradiction with Newton's second law that says that the net force on the system is zero, so the acceleration of the system should be zero. And so indeed what we find is that the center of mass velocity of the system, the center of mass acceleration of the system is zero. And we can see that by recognizing that the velocity doesn't change. The center of mass velocity doesn't change. It's not the velocity of the system, it's the center of mass velocity, because you can only talk about the velocity of a place or of a single object. So we have to talk about how the center of mass moves. All right, so perhaps the last thing to talk about today is the center of mass frame. So the center of mass frame is basically, remember when we were talking about like reference frames way back in the day? The center of mass frame is just a choice of reference frame that follows the center of mass. And it just makes, it allows you to simplify otherwise complicated systems. So let me give an example. Consider an exploding projectile. And we're going to model an exploding projectile as a projectile that is broken up into two halves by a spring. So initially, you launch your object, and it has two springs, or it has two halves, and they're connected by spring. You launch the object, it goes up, and then when it's at the top of its arc, it splits up into two halves. Now, this one half will drop here. This other half might drop here. But the center of mass is going to go somewhere else. Right? The center of mass will be wherever it is. So let's say that this distance here is measured. Let's say we get out a ruler and we measure this. And we don't know this distance. We don't know the distance that the other half goes. How would we find that distance? Well, come on, scroll, will you? To find R2, we can use what we know about projectile motion to find the position of the center of mass, right? So we know how to find the distance that a projectile travels. So the idea is just work in the center of mass frame. And what that means is just follow the center of mass as if it was all just at a point. So that would just go in an arc like a normal projectile would. And that would tell you where the center of mass lands. And then from there, we can solve for R2 using the definition of the center of mass. So if you know where the center of mass is, and you know where one of the halves fell, you can use the definition of the center of mass given up here to find the position of the other object, of the other half. And so this is just a way that using this idea of center of mass can otherwise solve complicated problems, because otherwise you'd have to consider, okay, what force does each half experience during the separation event? No, you don't have to worry about that at all. As long as the center of mass experiences no external impulses, that means that the center of mass is not changing position before or after they separate. And so because the center of mass is not horizontally, it's not changing positions horizontally. Because the center of mass is not changing positions horizontally, you know that wherever the center of mass lands, sorry, you know that the center of mass is not affected by the separation event. And so you could use projectile motion to solve for where the center of mass would have been if there was no separation. And then because there's no external forces on this projectile in the horizontal direction, the center of mass of the two separated things will be in the same place. You can solve it if you know the mass of the object, but not the location of the center of mass. No, not necessarily, because you'd have to. Oh well, okay, yes. Yeah, if you know that they are both equal mass and that they go off at the same velocity in either direction, yes. But this method works for significantly more complicated problems, like if you only shoot off like a third or some arbitrary percentage of it on one side and the rest on the other side. One caveat here is that this separation must have occurred in the horizontal direction. There can be no additional imparted momentum in the vertical direction, because that would affect the result here. All right, so I'm going to end it here. I know I threw a whole bunch of stuff at you.